Hello, everyone. We are Group 19 and here to talk about the virtual dice rolling. I'm Benjamin, and with me is Karsten.
Hey.
Robert.
Hello.
And Yitzi, who's currently not here. Our problem statement for this project is a means of virtually rolling a dice with stimulated mechanical movement to avoid the spread of germs and allow the use of dice without physical limitation. A little bit of background on our project. We'd like to minimize the spread of germs, given that its particular entrance currently in the world, given the ongoing pandemic. Looking to remove contact with these non-noticeable germs is key to stop the spread, as the Cystic Fibrosis Foundation points out that germs can indirectly spread through the sharing of physical objects. Objectives are to remove the spread of physical contact germs from activities involving sharing of dice. This is application in board games with friends, as well as casino activities. As a bonus, we'd like to allow for a completely flexible dice specification without mandating a different physical dice. For instance, we can have a 7-sided dice or an 838, or you can roll 1 or 2 dice, or even 97 simultaneously. Needs for this project are to roll a virtual dice given mechanical input, as well as communicate the results of that roll back to the user. And some non-essential needs for this project are to add a visual appealing container to house all the electronics, as well as to add sounds throughout the runtime of the device to make the use of it more satisfying. Functions, we'd like to allow for the user to input the number of sides of dice to be rolled, as well as the number of dice to be rolled, and this can be an input of 1 or 999 for either or, allowing for freedom to the user to specify. We like for the device to detect the shaking hand movement of the user and nothing else within the range of the sensing module. This is so that it doesn't pick up any background motion while it's idling and take it as a user input. We'd also like for it to output a random number within the range of the size specified by the user. And now I'll pass it off to Robert.
Hi, I'll be going over the system architecture for our design. There are 5 main modules that are implemented during the running process of our device. This is the order that they're performed: the display output, the user input, the motion detection input, the random number generation, or RNG for short, and the display output again. The sound module is found at various times during this process. The display output module introduces the startup screen to the user and gives the information needed to operate the device. It relays inputs that the user made back to them as a confirmation in their wanted values. It also displays a sequence of all the values of dice that have been rolled from the RNG module. The user input module takes 2 inputs from the user. It stores the first number as the number of sides of each dice, the number of sides each dice will have, and it stores the second number as the amount of dice to be rolled. It sends this information to the RNG module. The motion detection module is essentially a gatekeeper for the RNG module. Once this module detects a shaking hand above the device, it gives the go-ahead for the RNG module to be executed. This is the same manner in which a normal dice is rolled. Someone rolls a dice and then gets the number after the dice has been rolled, not the other way around. The RNG module provides a random number within the constraints of the dice configured by the user. The number generated would represent the result of a physical dice roll. To generate a random number from instance to instance, we seed the generator using an onboard timer. It takes the time taken in milliseconds to configure the dice specification as seed values. This makes it hard to replicate the seed. The module then makes use of the random function to generate the number and output as a dice value. The sound output module provides sound effects to make the device more satisfying and interactive. This module uses an amplifier in conjunction with the speaker to output various tones. The software uses timing of multiple tones to generate a few melodies that get played at certain points in the run process. I'll now pass it off to Kirsten.
Yeah, so in terms of system performance, the virtual dice roller exceeded all expectations set by the problem statement. Unfortunately, there is a lot to discuss here that we don't have time to cover in detail in this presentation, but thankfully that can be found in the supplemental final report. The system is capable of rolling 999 sided dice. This is limited by the C language. There are workarounds to allow for more, but we felt those were more than sufficient numbers. It does these rolls blazingly quickly. The cruel thing about random number generation is that to do so, you must first have a random number. This is called encoding or seeding using generated entropy. To generate entropy, the device counts on a scale of milliseconds the time it takes for the user to input the dice specifications, functioning as a pseudo-random number generation, as mentioned. We solved any troubles regarding detection issues with simple smart positioning of the PIR sensor in a cone above the hardware. We also met the non-essential needs of a beautiful ASCII animation display and sounds throughout to highlight key checkpoints in the roller's use. For every module in the system, we prototyped a placeholder to run on a PC operating system and tested it thoroughly. As that was happening, we tested an equivalent module using the appropriate hardware until neither had any bugs. When that was the case, we replaced the placeholder with the hardware equivalent and then tested the entire system for all extreme cases until no bugs were found. This method allowed us to find all limitations of the program and prevent the user from accessing them as necessary.
For testing of the user input, we used the USART port connection with a host computer as well as an oscilloscope. The USART allowed us to confirm that the inputs were what they were inputted by the user, and the oscilloscope allowed us to test the interaction between hardware and software.
Here's the module testing for the motion sensor. Once it's powered, the PIR sensor outputs a high signal when it detects something. There are two screws on the side of the PIR sensor, one for sensitivity and one for timing delay. To test it, we connected the PIR sensor output to an LED and adjusted the screws so that the LED would turn on and off quickly, sort of like a short pulse. We also made the time delay about 5 seconds. This is so the software could read it as a pulse and not make a double roll.
For testing the RNG module, we compared the seed versus non-seed, and we attempted to replicate the seed as well as compare the results of the RNG from instance to instance. Looking here, we can see that with the seed, the numbers are random, and without the seed, the numbers are consistent in each instance. As well, with the seed, the numbers of the dice roll are different from instance to instance. For testing, furthermore, for testing, if we can replicate the seed, you can see here over 30 trials, we got close once and we actually replicated it twice, or replicated it once later on attempts 23 and 34. However, we weren't consistently able to continue this pattern, allowing it hard or making it hard to consistently cheat by getting the same seed. For testing the sound, it was a combination of trial and error mixed with guess and check. We would do this to try out frequencies and see if they sounded nice together. And if they didn't, we go back and try a new one.
The feasibility of the project speaks for itself. It was implemented in its entirety to meet all essential and non-essential needs, which it does consistently and reliably. We also think that it is useful. The roller allows impossible combinations, or simply combinations that the user can't create in terms of number of sides or quantity of dice. It does all that without spreading contact germs during a time in which the spread of germs is a big deal. We also believe that the device is innovative, or at least we know of nothing like it. It is creative and has huge potential for future work to be revolutionary. There are a few things that could be added to the roller outside of the scope of this project that would really bring it to the next level. For instance, an LCD or LED screen with a battery would make the device totally transportable and discreet. A completed case with more materials would go along with that to create a more exquisite case with custom components to match its aesthetic. And finally, the big one, specific games could actually use the system we've created as a module within them, allowing more complex board games to be played virtually, benefiting from enhanced tracking systems without losing the physical aspect we all know and love. But that does it for the design of the virtual dice roller in this class. We hope that you loved hearing about it. Please watch the video demonstration to see Robert play Monopoly and read the final report for everything we've talked about now in more detail. Thank you.